Welcome everybody in the lecture hall, welcome everybody on Zoom, welcome everybody from the future for this special day of celebration. It's the end, the final lecture of the semester. So I have one last module, but very short and just a few high-level considerations on the physical implementation of PostgreSQL, and then I'll move over to some wrap-up of the material. I'll tell you a few words about the exam, and then we'll proceed to the big quiz game with a prize to win. You might see here, thanks to Marco Schöb, we have a trophy. And so the winner is going to leave with this trophy. So I have told you many times about data independence. It's this idea that the user of the database should just see tables, the relational model, and the user should just write SQL queries that manipulate the tables. With the relational algebra, you can select, project, aggregate, join, and so on. But of course, all of that is not magic. It has to be implemented somewhere. And actually, there are engineers that spend years and years of hard work implementing the database system, the database management system known as PostgreSQL. Typically, the sort of languages they use for that can be Java, C++. I think this one is in C++. I'm not entirely sure. But basically, these people had to use an imperative language. They had to do all the hard work of explaining to the computer how you join, how you select, how you project. They had to go through all the hard work of storing a relational table as bytes on the disk and of implementing how the query is optimized, executed, and so on. And of course, that is a lot of very hard work so that the end users don't need to worry about it. They can just write their SQL query. And so in this part, I would like to tell you a few details about how this was done, but just on a high level. So whenever you interact with a database, in the good old days, it was with clay tablets, right? So all the processing was in the human brain. But now we have electronic components. So you probably, many of you are familiar or with what they look like. So the CPU is this little square like this. This is the actual brain of the computer, right? This is all the silicon and transistors that process the data. And in fact, these CPUs do have a bit of storage, very little, but that storage is very close to the processing. So this is the most efficient, the most expensive as well, part where you have, it's basically the data that is being processed right now by the CPU. Then you have the memory, the RAM. You've already heard about RAM, right? Random access memory. It's basically the one that you lose when you switch off the machine, right? That's the one that you need electricity for in order for the data to be preserved. It's also rather expensive compared to a disk, but it's faster to access than the disk. And so this is why it's also called working memory. And volatile on the right really means that if you cut the electricity, that's all gone, right? And then you have the non-volatile memory, that is the one that stays in the long term, even without any electricity. So you have the disks. So nowadays you have two kinds of them. You have the mechanical drives, where you have mechanical parts that rotate, right? These are a bit slower, but they are also cheaper. And then you have the new kinds of disks, the flash drives, where SSDs, where it's much quicker and there are no moving parts, nothing that moves. You probably noticed on the laptop that it's less noisy. And these, you don't need electricity. You can preserve over the long term. And finally, you have the cheapest form of storage ever. These are the tapes. Now you're going to tell me that still exists. Yes, absolutely, that still exists. In fact, your backups, if you store data on your ETH storage servers, ETH backs it up on tapes somewhere in some facility. And typically in these facilities, you have some little robots that move the tapes over, and you know, it's the cheapest you can have, right? So this is for backups purposes, because of course, if you need to actually access the data, you need the little robots to go there and fetch the tape. It takes a lot of time, right? So it's much slower than when you actually use the database with the disk and the memory. Okay, so this is the D of ACID. Remember ACID, right? When I told you about transactions, D is for durability. This is for keeping the data over a very long term. And so as a rule of thumb, the higher you get here, the more expensive it gets per byte. And also then, as a consequence of being expensive, the least you can have, right? So if you look at the CPU, you just have a few megabytes. The access is also very fast, nanoseconds, because you're very close. In the RAM, you have, so the smallest laptops or computers today have 8 gigabytes. Most of them have maybe 16 or 32. If you go to the data center, that can go all the way to a few terabytes of memory, of working memory. That's a lot of memory. The access is slightly slower, takes a 2-digit or number of nanoseconds. Then you have the disk. Here, you know that's what you buy in the shops when you purchase a computer, right? So the smallest ones nowadays have 256 gigabytes. You have 512, 1 or 2 terabytes. And then in data centers, you can have even larger ones. And here, you basically are talking in milliseconds to access the drive. You see, it's already a different order of magnitude. And then the tapes are terabyte, petabyte, very easily. You can store a lot of data. That would be a lot of tapes right here. I'm talking about the entire facility. And then it can take seconds or minutes or even hours in order to access it. Why is that important? Because the number on the right that you have, when you do a lookup on your database, you want to access the data, this is how fast you get it. Right. So if the data is already in the memory or even in the CPU, it's super fast. If you read it from the disk, it's a bit slower. But again, with indices, you can have a few milliseconds. Anything that's stored on disk, within a few milliseconds, you can access it. If the index tells you where you find it, of course. Okay. So this is the capacity. Now, as you imagine, PostgreSQL is storing everything on the disk, right? Whenever you have a relational table, as it magically appears in your notebook, it's actually stored when you retrieve it. That's the from clause, right? When you say select from a table, that table is taken from the disk. So of course, it's going to be directories and files. In fact, if you're curious, you can look it up. It's somewhere on your hard drive in some PG data directory. You will see directories and files. And it looks like this if you actually go there. That was taken on a Mac. But basically, you see all of these intriguing directories starting with PG underscore, PG for Postgres, of course, and containing all kinds of stuff. And of course, as a user, you should never have to actually look at it, right? This is only for the curious or for the actual implementers of it. But this is what you have behind the scenes that is nicely hidden. And what happens is that PostgreSQL is going to store every record that you have in one of these tables. Remember that a table is a set of maps. Every map is also called a record or a tuple. And what is a tuple? It's basically made of several values that are all associated with a column name, right? With an attribute. Remember, you can see these records as maps from the attribute name to a value. So here you have four attributes that are mapped to 4 values, if I consider this one. Now, how is it going to be stored physically as bytes? You just concatenate everything. So you're going to have the name here that is converted to bytes. You have ways, if it's a string, for example, to convert the letters to sequences of zeros and ones, sequences of bytes, then the address, the gender, and the birth date. And then you have all kinds of additional, that's called metadata, additional things that the database system stores in order to make sure that it can read it back, right? So all kinds of extra information, right? So for example, here you store the number of attributes and you know how many these are and so on, right? Now, there is a difference depending on the attribute types. There are some attributes that always take the same size. For example, if you're storing an integer on 32 bits, these are the numbers between 0 and 4 billion, then that takes 32 bits. It's always 32 bits. So that's the number of bits you need on the disk is always the same. So these are a bit special, and you basically store them first. All of the values that always have exactly the same physical size, you store them first like this. A date is the same thing. A date always has the same number of bytes. It's a year, a month, and a day. So this doesn't vary. And all the values that might vary, and that's typically when you have varchar, that you know this is going to be a varying, var is varying, right? And these you actually put at the end because it's elastic. Here the size is going to vary because that depends how long your value is, right? And so you put them at the end and you add at the very beginning some pointers that tell you where to find them and where they stop, right? And this is the part that varies. It's just for efficiency reasons, because when you have a fixed size, somehow it's much easier and faster to access them because you know exactly where to find them. When you have a variable size, it's more complex. Imagine in order to know where to locate the address, you need to know where name ends because that's varying. And this is why you need this extra information right here that tells you exactly where address starts. For whom is that clear? Right? So it's the sort of thing that the system has to figure out. Of course, when you sit in front of your notebook and type SQL, you don't worry about that. But the engineers who implemented PostgreSQL, they worry about that. And then there are the very large strings and the very large objects. Imagine that you start storing images as bytes into your table or videos, like larger things. Well, first, normally, this kind of system is not designed for that, right? When you sort data in a relational table, it's supposed to be atomic, it's supposed to be small. But some people need that. Some people need to store larger values in their tables. And so PostgreSQL at some point was extended to do it with a reasonable performance. And the technique that they use is called toast. And the reason it's called toast is just like when you have the toast, you slice them, you know, like this. And this is exactly what it does. It's going to take this huge image or this huge string, it's going to slice it. And then there is somewhere, some special table somewhere else that has all the slices of the entire database, right? And they are stored separately. And when you want to retrieve the values of the image, it just retrieves the slices and glues them back together to get your image, right? So it is capable of handling the very much larger values, but it took a bit more work. Of course, for the very large values, some systems on top of clusters with HBase or similar systems that we cover in big data might make more sense than such a system. Okay, so these are some of the evolutions that came later. Really like the name Toast, that really indicates everything that it's doing. All right. Now, I told you about single records, right? This is one record that is stored as a concatenation of all its values. And by the way, all of the records in the same table will have the same attributes, right? That's because of relational integrity. So when we actually store these, we're going to store millions or billions of these with exactly that same structure. Just the size might vary a bit because it's elastic, right? You have some of the values that might be longer or less, but the structure is the same. Now, PostgreSQL could, if you do it naively, whenever you add a record, you could just ship that record to the disk and write it to disk. The problem is that the records are rather small. And a disk, especially a mechanical disk, needs time to move. It's very inefficient. Whenever you read or write to the disk, you have to wait until it rotates to the right location and the reading head lands on top of it. So a computer is not going to do it bit by bit or small records by small records. It's going, on the contrary, to wait and accumulate a few of them and then write a lot of them at the same time. And this is done in what's called a block. And a block is basically going to have 8,000 characters, 8,000 bytes or 4,000 bytes. It's just the order of magnitude that matters, right? So a few thousands of bytes. And that is considered efficient for a typical laptop or a typical computer. So we read and write to and from the disk a few thousands of bytes at the same time. That means that it's going to be more than a record. It's going to be multiple records that are written to disk at the same time. Right? So this is called a block. PostgreSQL calls them pages, but it's the same idea, right? All right. So by the way, it's the same way that, why is it called page? When you want to print something, you don't print every word by word to the printer. You print page by page, right? When you print, it's a whole page. So it's a little bit like this. You have to accumulate enough to fill a page, and then you print the page. So this is why it's called a page, except that it doesn't print. it puts it on disk. All right. Now, what does a page look like? Well, it's made of records. What is interesting is that PostgreSQL starts on the right at the end and puts the first record at the end of the page and then adds the records like this, making its way back. All of that is done in memory, right? In memory, PostgreSQL is accumulating the records, and when a page is full, then it's going to write it to disk, right? So this is at most 8,000 characters, 8,000 bytes, right? All right, and then you have a place that's called record offset, where you know where the records are actually located, right? You have some numbers. It's just a distance, basically, that tells you here is this record, here's this record, here's this record. That is a page. And then, in a single go, you write all of that to disk as a page, right? And that is efficient. Then, of course, you need many, many pages for a table. And since one page is 8 kilobytes, and on disk, we consider that a size can be, for it to still remain efficient, we can go all the way to a gigabyte for a physical file written on disk. Then it means that one file on the disk is going to be made of 125,000 pages. That's basically because if you divide 1 gigabyte by 8 kilobytes, you find 125,000 pages. So again, this is one file. If you look on the hard drive, you will see one file that is a gigabyte, has a size of a gigabyte. And these pages are just for reading and writing to the file, right? It's going to write in these chunks of 8 kilobytes, but that one file has at most a gigabyte, right? And then one table is made of plenty of these files. These are called chunks. So in that case, we have a table that has 1, 2, 3, 4, 5, 6, 7. So it's somewhere between 6 and 7 gigabytes here. So the first ones are exactly 1 gigabyte, and the last one might be a bit less because that's the last one. So here we have one table that is worth 7 gigabytes of data, right? Nicely divided in files of 1 gigabyte each, and each file is nicely divided in pages, which are the atomic blocks in which the computer is writing and reading from disk. Who is with me? Right? So this is the magic. And it looks complex, but this is precisely because it's complex that we have data independence and that you don't need to care about that, right? I just told you for your curiosity. As a user of PostgreSQL, you don't care. That just works in the background, and PostgreSQL is taking care of all of that. All right? Okay, so that was actually the last slide. That's all I wanted to tell you, to make you aware of what's behind the scenes. And the reason, basically, if you want to use Python or Pandas or libraries like this without a database management system, then you have to deal with it yourself. If you use Python or Pandas, you have to say, read that file from blah, blah, blah.csv, write it back to CSV, and so on. It's your burden to actually deal with the files. So this is one of the benefits of a database management system, that it does it for you. Any questions? All right, that was very high level. Of course, it's even more complex than that in reality, but just wanted to give you an impression. So I'm going to stop the recording here.